Perfect. Awesome. Yeah, thank you so much. So my goal for this talk is to do just a bit of an overview of what explainable AI is with a lens of talking about it from a UX perspective. So thank you for that introduction. Yes, I'm Meg. I'm a UX researcher, a user experience researcher at Google. I've always worked on Google Cloud, and about a year ago, I started working on cloud AI and industry solutions. We have a number of products and features for Google Cloud customers to sort of help them from end to end for a variety of different machine learning experience levels, data science experience levels, to make it easy for you to train and deploy machine learning applications. And for the past year, I've been really focused on our explainable AI services. So we have a number of them. And for this presentation, I'll be talking about explainable AI in terms of just the basics, like what is it? What's some of the vocabulary and the terminology you can find when you're looking up explainable AI? Why is it important? What's essential about it when we're talking about machine learning applications? There's also a number of regulations and conversation we brought up earlier before the talk about trustworthy AI or ethical AI. There's a lot of conversation in the sort of standard space and the regulatory space about explainable AI that I'll just briefly cover. And then I'll talk about, of course, the human audience. So the one thing that's really interesting about explainable AI is, you know, it's like explaining machine learning to a human of some sort. So making it understanding to humans. And there's a lot of interesting facets to that. And then just sort of towards the end, I'll talk about like, so how should we approach it? If you're a UX designer or a UX researcher, what are some things that we could think of or we could bring to the application development process when it involves machine learning and explainable AI? So first, the basics. So explainable AI, in a nutshell, is the endeavor to make machine learning models more understandable to humans. And you've probably already heard some definitions around the space, in particular transparent and opaque, or sometimes it's referred to transparent and black box. One set of definitions for this is that a transparent model is one that reveals its internal mechanisms, and an opaque one is one that does not. But you can, if you look across the literature, there's lots of actually varied definitions for these terms. One definition for transparent is that it's a model that's by itself understandable and that you don't need anything additional to explain it. Whereas an opaque model is one that you need some kind of post hoc explainability technique to try to understand it. And even when you try to think of like what qualifies as transparent, there's some pieces of literature out there that say, oh, if it can be simulated, or if you could decompose the algorithm into different parts, or if it's just algorithmically transparent, as in it's very well understood, then it makes it transparent. But I presented this to some internal folks at Google, and they were like, yeah, well, actually, if you can, any machine could step through every like process of a DNN network. Like if you had infinite pieces of scratch paper, you could go through the algorithm of creating a deep neural network. But so there's sort of like some sort of threshold. And actually, when you look at different types of models, a lot of times there's some types of machine learning models that are generally thought to be transparent. So like regression models, decision trees, support vector machines, for example. And then there's other types of models that are generally thought to be opaque, like tree ensembles, deep neural nets, reinforcement learners. But actually, decision trees, for example, are generally thought to be transparent. But if your decision trees are really complicated or get very, very deep, then they actually sort of become opaque, don't they? Because you can't actually logically step through them, or whatever equation you would produce to explain an explanation is just too convoluted. Same thing for support vector machines. If the Support vector machines are interesting because if your data is really messy and complicated, your resulting support vector machine is also going to be very messy and complicated. Whereas if your data is really clean and nice and well organized, then, or sort of like naturally has these boundary lines, then your support vector machine is going to be very clear and easy to understand. And then on the flip side of that, tree ensembles, generally we think of as being too complicated, but if the trees are simple, it could be, maybe you would consider it transparent. So I put this up there to say that I think a lot of times people think of transparent and opaque as just two very clear-cut categories, but actually there's a lot of gray fuzziness in between. And also the terminology around explainable AI itself is frequently messed up and words are used interchangeably. So there's these words interpretable, explainable, and comprehensible. And if you look at the literature, if you go and search in academic papers, every academic paper publishes their versions of the definitions, and the definitions are not the same from paper to paper. But one way that I've sort of adopted for these terms is that interpretable is a sort of passive characteristic. So if a machine learning system is interpretable, as somebody can understand it, then that's interpretability. Whereas explainability is more of those post hoc techniques that you apply. I think of it as more of an interface between a machine learning model and a human. The explainability is sort of the layer in between that will hopefully make your ML system interpretable. And comprehensibility is interesting in that refers to whether a machine learning model can take what it has learned about the data or the world or otherwise and present that learning in a human understandable fashion. But like I said, it's sort of word soup if you go into the academic space, but this is just one set of definitions to work with. And we brought up trustworthy AI earlier, and one thing that's interesting to me is trustworthy AI is not just interpretability. There's actually many facets to trustworthy AI. You can talk about the robustness of a system, the accuracy of a system, fairness, of course, that comes up. We talked about ethics earlier. So does your system have biased outputs for different parts of the population? Things like accountability. So who's responsible for the system? Who is responsible for the data that went into training this model? Transparency, is it clear to how the system produced its output? And other facets. So interpretability is just one possible component to trustworthy AI. So in the next part, I'm actually going to talk about some very specific explainable AI techniques. There are a number of them, and this is a field where in the computer science space and the machine learning space, people are actively creating more explainable AI techniques. A couple to know about is sort of explanation by simplification. So that is if you have a very complex machine learning model, if you do some rule extraction, you can sort of simplify how the model's behaving and present that simplification. One technique that's very popular is this second one, feature relevance explanation. So it shows you which features, like how each feature in your data influenced the prediction output. And this is actually an example of visualization. One popular flavor of this technique is called Shapley values. I will be not be getting into the details of how Shapley values work, but this shows you, if you imagine each one of these lines is a feature in your data, it's showing you how much it contributed or detracted from the prediction score in this output. And then there's other techniques that are more visual, provide explanation through a visual representation. So something like LARP, or something that you overlay over top of images showing you how the model behaved, would be an example of that. There's a couple more. One is called explanations by concept. This is a really interesting one. There's one called TCAV, or testing concept activation vectors. And this image is an example of that. It starts with you as the machine learning developer defining some concepts a priori. So for example, if you're working with image data, you can work with the system to define a concept called striped. So you could say there's a pattern called striped. It either looks like this or it looks like this, and that's striped. And then once you have that concept defined, you can use TCAV to say how much did stripedness contribute to the prediction of what this image is. And so for example, striped contributes a lot to whether we predict if it's a zebra or not. And so that's a really interesting way to go. And then the last one I'll talk about is explanations by example. So instead of telling you anything about the features or any concepts, it says, we got this prediction value for this particular piece of data. And here are the 10 approximate nearest neighbors in your training data set. So it sort of lets you know by analogy or through example, what this piece of data was similar to in your training data set, which is an interesting technique. And this is an example of how that could possibly work. So let's say you have this image of a bird, and let's say you're training a model to identify birds versus planes, and you get this image and you say, hey, my model misclassified it as a plane. And you use something like example-based explanations, you can see, oh, all my nearest neighbors have this sort of silhouette type image. Maybe if I added more pictures of birds in silhouette, my model could be retrained and it would be better able to identify this type of image. And another thing I want to mention is that explainability methods could be either model agnostic or model specific. So that means exactly what you think it means. Model agnostic means it can work with any type of machine learning model, pretty much. Model specific means it's been designed to work with a very specific model machine learning technique. The other thing to keep in mind is that explanations could also be provided at different layers of granularity. So a local explanation means that it's only providing an explanation for a single piece of data or a single prediction. A cohort is more like this, where you have a group of predictions and you say, provide an explanation for this cohort or a subset of predictions. So imagine in a scenario where you had a bunch of data and you were like, actually, I just want to see what the explanations were for all of this population in this particular county in Pennsylvania or something like that. You could choose a meaningful cohort and see if you could get explanations for those predictions. Whereas global explanations provide an explanation on the model decision-making process in general. So why is it, that was sort of like the explainability 101, and why is it important? And there was this really great quote from one of the papers I read when I was composing this literature review. And it's, the danger is in creating and using decisions that are not justifiable, legitimate, or that simply don't allow obtaining detailed explanations of their behavior, which I thought sort of summed it up. Why do we need explainability at all? And looking across, there's all sorts of application areas where explainability is very important. So when you think about the development, assessing, optimizing, and troubleshooting machine learning systems, you really need explanations when you're trying to complete tasks like, why is my model making inaccurate predictions for this particular data or this particular set of data? There are a phenomenon called like data skews, like data can skew or shift over time. So your model can start performing less and less well as data changes over time. And without knowing the why behind certain prediction decision-making, it's sort of difficult to diagnose what's actually happening there. There's also a lot of application areas for feature engineering and data pipeline optimization. So for example, if you find out that actually there's certain types of data features that don't seem to have any influence whatsoever on your machine learning model the way it makes its predictions, then you can actually try to remove those features from your data to sort of optimize your storage costs, optimize your data pipeline, and see if your model performs just as well, like without that type of data in there. But it's really hard to make those kind of decisions if you don't actually know what features are contributing to the model predictions. And there's actually a really great article that sort of describes how you need different levels of granularity of explanations for different parts of the machine learning lifecycle. So from the initial training to validating to troubleshooting when it's actually in production, you need different granularity. So for example, this one's showing like beforehand, I just need a global prediction. But as you start validating, you might want to say, I want to make sure my model performs just as well for those under the age of 30 versus over the age of 50, sort of checking for different biases maybe. And then maybe as you're troubleshooting something, you might actually have sort of a mix of things. You're either troubleshooting a very specific application or a certain group of things are not performing well. You'll need a variety of different techniques in order to troubleshoot. And we sort of talked about this earlier, but it's really important to assessing fairness and addressing bias. So models, as I'm sure many people on this call know, they can arrive at unfair, discriminatory, or biased decisions, but without any understanding of the underlying behavior of the model, it's hard to assess and it's hard to fix. And it's also just essential for end user adoption. So in general, people are reluctant to adopt or use technologies that they don't understand. And sometimes being able to use an application requires an understanding of the underlying decision making. So for example, imagine in your head a digital pathology tool where there are certain samples and it makes a judgment on whether a patient has a certain condition or not. Let's say it's cancer. A pathologist is not going to just say, hey, the machine learning model says you have cancer, so you have cancer. They're going to want to know why the machine learning model flagged that as a potential risk factor for you. They're going to want to examine the features that led to that prediction so that they can actually use their expertise and judgment to make an ultimate diagnosis for their patients. And one other area I'll touch on is sort of the more regulatory space. So there are already existing regulations. So for example, in financial industries and government applications, there are already regulations requiring explanations for how decisions are made. So for example, in the US, there's the Equal Credit Opportunity Act, which means that anytime a lender has an adverse action, so that could be you're rejected for a loan or something like that, they are required to be able to provide a detailed reasoning for that. So if they're using machine learning models, they need to be able to provide sufficient reasoning for those type of notices. And in the EU, for example, citizens have a right to have reasons for any decision that the government makes towards them. So for the same sort of reasons, they have to be able to understand if they're using machine learning, why were certain decisions made for these citizens. There's also, I think probably many of you have heard of GDPR. So that's why we have the wonderful little banners that make us accept cookies on every website. That's one of the many claims to fame of GDPR. But in GDPR, there's already some language around how you shouldn't be subject to only solely automated processing, including profile, and that customers have a right to obtain human intervention or express their point of view and contest any decisions. And also has this line of customers have a right to meaningful information about the logic involved, which is sort of interesting phrasing. And there's also these draft regulations coming up in the EU. There's the EU Artificial Intelligence Act, which specifically is talking about high risk applications. And there's a lot of language around what qualifies as high risk. But for high risk applications, they require a certain degree of transparency, that users should be able to correctly interpret system output, and that they not only should they be able to interpret it, they should be able to use it appropriately. So there's actually a lot of UX sort of bundled into that regulation about being able to interpret and use a machine learning system in those high risk areas. And of course, in the United States, we have our own standards boards and our own regulatory agencies, and they've all published like a number of white papers about trustworthy AI. And these are sort of 3 bullet points that I pulled out from a lot of those white papers. And that is that explanations should be understandable. So if you're explaining a machine learning system, whoever it's intended to go towards should be able to understand it. The explanation should be accurate so that they should actually reflect what the system is doing. And then they should convey limitations. So just like anything, any measurement tool, any system, any application, you know, there are application areas where it works really well, and there's other areas where it should not. So if you think about like taking a general thermometer, you know, it's not going to work in sort of subarctic temperatures or something like that, the run-of-the-mill thermometer that you buy. Like every system has its limitations, so your explanation should convey that. When are the moments where you can trust the system? When are the moments where maybe you shouldn't? And this was another great quote that I pulled out. So as more and more regulation impacts technology, companies are not going to be able to hide behind ML black boxes to make decisions. If they'd like to reap the benefits of machine learning, they're going to have to invest in solutions that provide explainability. So this was a great article, and it sort of just brought to bear that we're in this sort of wild frontier of machine learning, but that explainability is very quickly coming to the forefront of concerns. And now we'll get to the fun part, what I consider the fun part, which is considering all the humans involved. And so again, I'd like you to think about in your mind a digital pathology tool that uses machine learning to help a pathologist make diagnoses about patients. So if you consider in that scenario, you have people who are the machine learning experts. So you have the data scientists and the model builders. They are probably experts at machine learning, but they're probably not an expert at pathology data. Whereas you have the pathologist who's definitely an expert in pathology and knows exactly how those samples have been collected and the reliability, but they're possibly not an expert at machine learning. And then you have the patients who are probably not an expert at machine learning and probably not an expert at pathology, but they are also impacted and affected and sort of need to know how the system is behaving because it has ultimate impacts on what's going to happen to them next. And I found this paper and it had a really great analogy about how explainable AI is very similar to how forensic scientists have to explain their work and explain evidence to lay people, members of the jury. And they actually found that when these forensic science experts are trying to explain themselves to the jury, that oftentimes the jury leaves with misleading or confusing interpretations of what the forensic scientists just presented to them. So it's a really interesting point where you have these experts in the data or the machine learning, and even they like sort of explaining what it is to the end users. There could be this moment of confusion or misinterpretation of what's happening. And of course, everyone involved, from the machine learning engineer to the pathologist to the end user, everyone involved in that diagram I showed, they're all humans. So that means that they're all subject to certain psychological biases. So there's one bias you might have heard of, confirmation bias. So that means that if you have an idea about the world, you seek out and favor information that confirms your beliefs, and you sort of tend to mistrust any information that comes in conflict with that. And so if you think about machine learning, if a machine learning engineer, for example, builds an expectation of how a machine learning model behaves, and they get some explanations that sort of confirm their prior expectations, they're going to say, yep, it's good. Whereas if they get something that contradicts it, they might sort of discount it and not investigate it as fully. So that's one possible example. and of course, in that pathologist case, the pathologist, if they get a verdict that says, yep, it's exactly what you thought it was, they're going to be like, yeah, that machine learning model is working great because it's confirming what I believe already. Whereas if it contradicts them, even if the machine learning model is correct, they might not trust it. Sort of on the flip side of that is this phenomenon known as unjustified trust or overtrust. End users have sometimes a higher degree of trust than they should when explanations are presented. And actually this quote comes from a study that I really encourage you to read because it's a great study, where they took two populations of people. They took data scientists and they took sort of everyday people who do not have data science expertise, and they presented them explanations for a machine learning model in two different formats. One format was a sort of human readable sentence, like an English sentence. The other was a more mathematical looking formula, like X plus Y equals Z type of thing. And they found that in both groups, regardless of whether they had data science expertise or not, both groups had higher degrees of trust in the explanation that was presented in the mathematical format than the sentence. So it just goes to show that trust can sort of be manipulated by how we just present the explanation. So that's a really interesting phenomenon when we think about the UX of an explanation or how we present it. And then there's this other bias called knowledge shields, which is sort of a extreme version of confirmation bias. Knowledge shields actually comes from the learning sciences, which is like when you are a learner, you're a student, you build up your own sort of understanding of how the world works. And as you encounter information that might run counter to how you think the world works, you actually build up these increasingly complex rationalizations to try to hold on to whatever your reductive understanding of the world is. So if you have a belief about how the machine learning model works, yet you get contrary information, you can sort of like rationalize it and sort of hold on to whatever model you have in your head, whatever mental model, for a very long time. And what they found in the learning sciences is that educators can actually take different steps to really scaffold the experience of how to confront your own understandings and really put it out there and define it and sort of challenge your own understandings. So that's sort of interesting to me in thinking about the UX of it, like how could we help our users challenge their own understandings when they see an explanation of a machine learning model. And so this is my conclusion piece to the talk, is sort of why we need thoughtful UX in this space. Is there's certain ways of, when you're thinking about the design and evaluation of explainability methods, one way you could think of is sort of like a very technical evaluation of explainability methods. So is it actually using statistics and scales and measures that are appropriate for whatever context we're working in? Does it actually produce valid results? Does it provide, if you have the ground truth and you compare the explanation method against the gold truth of an explanation, do they match up? And can you decide between, can you actually judge or have some kind of metric that lets you know when an explanation is good or when it's perhaps not so good? But one important property of being an explanation is that it's not a property of statements, it's an interaction. So what counts as an explanation depends on what the user needs, what knowledge they already have, and especially the user's goals. And so there could be more user-centric evaluation of explainability methods. So is it actually understandable? Do people walk away with an accurate understanding of what the explanation is trying to tell them? Are they satisfied with it? Does it make them feel satisfied that it's been explained fully? Is it, can you actually use it? So if you're making a decision, does that explanation actually help you in taking further action or executing a decision? And after trustworthiness, so after interacting with an explanation, do you trust the AI model to an appropriate degree? So knowing that you can have overtrust and you can have undertrust, does interacting with the explanation actually land you somewhere in the right level of trust with a machine learning model? I think those could be the more user-centric evaluations we pursue. And so I have this sort of like thought piece. So when should UX get involved in regular, ordinary product development? And for all the UX people on the call, it's everywhere. It's at every phase of product development. And so I want to say, like, when should UX get involved in machine learning development? It's everywhere. So when it comes to collecting data, we know that collecting the data for your training data model, your training data set, actually heavily influences the performance of that model that ultimately gets trained. So I think that there's a need for people who are specifically tasked with caring for the user experience needs to get involved earlier and earlier in the machine learning development lifecycle. And I'll leave you with this sort of last article and last quote. There's this really great article that for many of you who went to grad school, you were probably forced to read it. And it's called Do Artifacts Have Politics by Langdon Winner in 1980. And in it, he studies how different systems, after they were introduced in the world, they actually changed something about society. So he actually shows how there were bridges designed in New York, deliberately designed to have low profile so buses couldn't get there. So it actually actively kept out the working class from these different parts of New York because buses couldn't navigate them. And then they studied things where maybe it wasn't so deliberately designed, but after you introduced machines that would automatically pick tomatoes off of the plants, it actually changed the way money was flowing through the farming sector of tomato crop growing. And so one quote from that is, consciously or not, deliberately or inadvertently, societies choose structures for technologies that influence how people are going to work, communicate, travel, consume, and so forth over a very long time. And one piece that he leaves you with is, by far the greatest latitude of choice exists in the very first time a particular instrument, system, or technique is introduced, because choices tend to become strongly fixed. And the original flexibility vanishes once the initial commitments are made. So it's sort of, to me, just like a reminder that you need to care for the user experience. You needed to care about what happens with your technology very early, and sort of more of a call to action of why UX people need to show up early to the party. And I'll leave you with, Google has published responsible AI practices that are really great and actually highlight all of these needs to think about those experiences very early in your AI development practice. And I think that's where my slide deck ends, and I would love to take any questions.